All right. Welcome, everyone. Welcome. Hi. Yay. Welcome to our session AIM326, Large Model Training on AWS with DLAMIs and PyTorch, featuring Pinterest. My name is Arindam Paul. I am a Senior Product Manager at AWS. And along with me, I have Karthik, who is the Engineering Manager of ML Platforms at Pinterest, and Zlatan, who is the Principal Solutions Architect, who works closely with Karthik and myself. So before I begin, can I have a quick show of hands? How many of you have direct on-hands experience training models with PyTorch? Okay, cool. Thank you. All right, so I hope you'll find it very useful. So we have a packed agenda for today. I'm going to be talking to you really quickly about the challenges of training large models and what they do for us. And then I'm going to turn it over to Karthik for the main topic, for the main content of this talk, and talking about how Pinterest does large model training. And he's going to be specifically talking to you about the goals of large model training at Pinterest, how it impacts their business and the architecture they follow, and the results and the impact that they have had to date. And then we'll have Zlatan talk to you about the solution architecture that we have implemented for Pinterest. And then we'll end up with some key takeaways and take questions. Okay? One thing as you'll notice, that the content of the talks gets progressively more and more technical, and you can probably see that from the way we are dressed, from me to Karthik to Zlatan. Okay. All righty. So large models are everywhere these days, right? There is like if you're on any kind of social media or if you're observing the news, it's everywhere, right? And they are getting pretty good in generating movies, generating text, writing books for us, generating music, generating code, right? Summarizing, doing chatbots, doing smart searches, like pretty much all of our digital existence and maybe our physical existence also are starting to get reshaped by these large models, right? So, and we are on the cusp of a like revolution, I'll say it for lack of a better term, and we can see that totally happening in terms of like customers such as yourselves who are continually pushing the frontiers of this technology and solving more and more interesting use cases. However, training large models also comes with its own set of challenges. The first one is large models require large amounts of compute and large amounts of storage, right? So you have to, with scale comes unique problems. For example, the single biggest problem that's affecting our entire industry, as most of you know, is unavailability of compute resources, specifically GPUs. We in Amazon, we have Trainium and we have Inferentia, and we are investing in silicon to do both training and hosting. However, in industry today, like there's an acute shortage of these chips. So what do you do? How do you get around it? Well, one of the ways of getting around it is to increase the efficiency of the chips that you have, making sure every single GPU hour counts towards your model training, right? So that's one problem. Along with compute, there's also the matter of data. Like large models require, as you know, petabytes of data to train. How do you host that data? What about the cost of the data? What kind of access restrictions do you put on the data? Are all problems that someone who's training models have to live with. During a training run, for example, you can also have issues of instability. Your GPUs might have OOM errors or some kind of errors. So you have to recover your training runs in time and make sure that your models converge in the right time, within a reasonable amount of time. So regular health checks and making sure your training runs are robust to failures of GPUs are a critical issue. Orchestrating this large amount of infrastructure, right, compute, memory, storage, right, towards your and enabling your model training, and enabling that it converges in the right amount of time with the right amount of accuracy is a challenge. And you're going to be seeing how Pinterest solves it in in a few minutes from now. So before I turn it over to Karthik, I just want to talk to you quickly about two specific AWS technologies that you'll hear more from Pinterest talk about. And this is by no means the only technologies that are being used. Like this is two among many, many technologies. And by the way, for those of you who want to know more, we have QR codes for like release notes and very specific at the last slide. So you can just scan it quickly so you don't feel pressure that you have to take pictures. So the first element of our technology are AWS deep learning armies and AWS deep learning containers, what we call typically as DL armies and DLCs. Armies, as you can imagine, are from the name itself, are essentially Amazon machine images that run on EC2 instances. Now, we have, for what's special about DL armies, that they're specifically curated, tested, secured, optimized for deep learning workloads. Okay? And so we do a lot of work to make sure that all of this, like when we create these armies, your deep learning functionality works out of the box. If you're training a model and you run it on Army, it's guaranteed to be running on an Army that's tested and optimized for AWS infrastructure, AWS compute, and AWS networking. Okay? So that we'd like to do the undifferentiated heavy lifting for you so that you don't have to do it. Okay? That is, and so to talk to you a little bit more details, so we have a variety of armies for deep learning. The first one, the simplest one, is the base army, where we essentially package, and it comes in two varieties, one supporting Amazon Linux and one supporting Ubuntu, for those of you like prefer one OS over another. So in the base army, we package the latest NVIDIA drivers with the latest EFA stack, which is specific for networking, OFI nickel, to get the best performance for nickel. Right? And these are optimized for GPUs, and it essentially provides for you a curated set of libraries pre-tested for you to install your frameworks, right? Or to run your own containers. So this is the base army. The layer above that, the next set of armies is essentially the framework armies and the framework containers, DLCs. So these have the armies and the base armies as well as a distribution of PyTorch or a distribution of TensorFlow on top of it. Okay? So there are PyTorch armies and there are TensorFlow armies. There are PyTorch DLCs. There are TensorFlow DLCs. There is one other type of army called the multi-framework army, where we have both PyTorch and TensorFlow coexist together, okay? Because some customers prefer it that way. All right, so base armies, framework armies, and then the DLCs are similarly, right? So PyTorch DLCs will have PyTorch in it, TensorFlow DLCs will have TensorFlows in it, and they're all kept. So one of the questions that we get from customers is, okay, how difficult is it to create it, right? Creation of these armies and DLCs are perhaps not that difficult. The real challenge is the recurring cost that you have to keep on incurring to keep them patched and secure and current with every new version of frameworks that come out, and which is like multiple times a year. Right? So, and we do all of that work for you, right? So when you pick one of our DLCs and DL armies, it's always guaranteed to work. Like everything is security patched, and like you have our vote of confidence on that army or DLC. And the third offering in this space is a relatively new one. Last year, we created a conda distribution of AWS PyTorch. And this is specifically attractive for those of you who have machine learning teams who would like to mix and match various versions of PyTorch with various versions of CUDA drivers, CUDA and NVIDIA drivers, right? To make sure like you get the best performance and the best functionality. As you know, right, oftentimes with newer versions of PyTorch, it is beneficial to use newer versions of CUDA that have not been approved by upstream PyTorch yet. Okay, so typically it comes in like the refresh happens in like relatively soon enough, but not at the same time. Okay, so we do all that testing and we make sure like you can mix and match and you can essentially use our PyTorch conda distribution for your machine learning scientist. Again, at the last slide, you have a QR code. You can scan it, and it'll take you to the website with full details and descriptions. All right. And the benefits of learning, as I alluded to briefly in the last slide, is like number one, it doesn't cost you anything. It's prepared for you to help you to do your job. much more effectively and efficiently, and essentially help you lower your total cost of ownership of like maintaining this deep learning stack. Second important point is it's supposed to be more of a blueprint, right? So even if you don't find DLRMs and DLCs completely usable in its shape, you can take it and customize it for your own use. Okay? Feel free to completely do that. Lots and lots of customers do it, right? This gives you just a blueprint that you can essentially engineer and customize for your business use. It's secure. Like we take a lot of care making sure like we scan daily versus the NIST CVD database, right? So and we patch critical vulnerabilities pretty regularly. And so bottom line is we want you to have the lowest possible TCO, right, to run your distributed training jobs on Amazon, right? So and these products are not new. They have been out there for a number of years, 2-3 years now. And we have thousands of customers using it across every single vertical, every single use case that you can think about. So that is that. And then the next piece of technology that I would like to talk to you about is AWS Batch, right? For those of you who are familiar, Batch is AWS's managed offering to run batch computing, right? which has traditionally been very popular in the high performance computing HPC community. In Pinterest, Zlatan and Karthik have implemented some pretty nice, unique ways of using Batch for model training that we'll hear from them soon enough, right? So essentially, very briefly, for those of you who are not familiar with Batch, essentially what you do is you essentially create a unit of work is a job, and then as a user, you define your job with a certain number of parameters, and then you essentially queue it in a queuing service, and then that gets spun off into like actual compute environments where the job is run and the results are returned. And this is like a really high-level a really high-level description of what Batch is. You have a lot of material online to search for it, right? But the high order point here is that it's amazing, and there are some very cool use cases with Batch for machine learning. And the abstractions here make it enable data scientists and machine learning practitioners to essentially do their machine learning without understanding all the intricacies of infrastructure and all the low-level stuff. Okay? So Batch and DLRM together create a pretty potent combination for you to like run your machine learning workloads. All right, with that, I'd like to turn it over to Karthik to talk about the Pinterest, their goals and challenges, and how they do machine learning distributed training in Amazon. Thank you.
All right, thanks, Arindam. Thanks for the introduction. Good evening. It's great to be here. So my name is Karthik, and I'm an EM on the ML training infrastructure team at Pinterest. And today, I want to talk about how we've built an infrastructure to train large models at Pinterest using PyTorch, DLRMs, and other AWS services. I'll first give a general overview about how training infrastructure works here, and then go over 2 case studies on how we've partnered with AWS to build foundational infra components that has helped ML engineers and ML platform engineers train large models. So the takeaway from this talk is less about algorithmic techniques, although I will touch upon it, but more so about how you can build foundational components that can help ML engineers train large models. So yeah, at Pinterest, our mission is to bring everyone the inspiration to create a life they love. The way we do it is through our content, and it all starts with a pin. A pin consists of an image, some description, a title. Instead of an image, you can also have videos. And what you can do with a pin is organize them into collections called boards. So here I have a board of expensive watches for all the watches I can't afford. And then, across the website, people have been curating pins into boards. What's very powerful about boards is that they represent very nuanced taste and understanding from our users. Take this pin, for example. User 1 is adding it to his wedding board, so it's probably he's looking to see how he can pair his watch up with his wedding attire. User 2, again, expensive watches. User 3 is interested in the brown strap of this watch. So the nice thing here is every user brings in a different perspective to that pin, and they're associating other pins to this pin. So this is what helps us build our Pinterest feeds. So we have home feed for the queryless experience. So when you first enter Pinterest, you're shown a feed of pins. This is based on your interests. And then you have search, where your input is text. And then we surface relevant pins. And then related pins, where the query itself is a pin. And we're able to find similar ideas to that given pin. Now, what's great is we have users curating and accessing Pinterest at scale. So because of the scale at which we operate at, we have a massively curated data set about how people organize and describe things. And as you can imagine, ML is at the heart of everything that we do. Just as a snapshot here, home feed, search, and related pins, and ads that we deliver are all recommendation problems. And for every pin that is shown, we are able to understand the pin itself. Is it a safe pin that we can show? We are able to understand images within a particular pin. So all of this is powered by machine learning. But broadly, we can categorize the ML problems into two. One is recommendation models. As I said, this is our entire feeds ecosystem. And then there's content understanding. The recommendation models are majority of our GPU footprint. They are transformer-based deep neural networks with embedding layers. And the inference characteristics of recommendation models is that one QPS for a feed typically translates into thousands of items being scored. And we have hundreds of millions of inferences happening every second. The other use case is content understanding. Here, we have models trained on the entire corpus. And as I mentioned earlier, one example is how do you know if a pin is safe or not? And the inference characteristic here is, it depends on the use case, but it could be a batch inference workload where all the pins, for example, are scored against whether they're safe or not. Or sometimes you may also need to do this at real time. And in terms of model training, for the recommendation use cases, they're typically trained on 7 to 30 days of training data. And they also require heavy data pre-processing, which I'll talk about. For the content understanding use cases, the model sizes do get bigger. And we'll also talk about how we can optimize training those models. Yeah, and what's powering all of this is, of course, data, compute, and smart ML engineers. And this is where ML training infrastructure comes in. We make it easy for ML engineers to access all this data, give them access to compute, so that they can take these models into production. We optimize for ML engineers' dev velocity and make sure they can move fast, efficiently. What's interesting is also the role that the number of ML engineers play. So doing ML with supporting ML at an enterprise with 5 engineers is very different from what you would do for 200 engineers. As an example, if an ML engineer is spending 1 hour every day on operations, those can multiply for 200 engineers, and you can see the amount of time that's being wasted there. Yeah, we've identified 3 main pillars for ML training infrastructure. One is ML application development, compute orchestration, and training hardware. I'll talk about each of these briefly. And each of these actually has a significant impact in how fast engineers can move and how efficiently they're able to build their models. So the relationship between these 3 pillars can be shown by what we call the ML stack. So what you see in yellow is the training application itself. At Pinterest, we package training application as a Docker container. The really nice thing about Docker is that it gives you full reproducibility. So if you have a model that was trained 3 months ago, you know the Docker image that was trained. That comes with the Ubuntu version, the Coda libraries, the PyTorch version. All of that is baked into the image. And the role that compute orchestration plays is, hey, you have this Docker image, and it's able to target that to a given hardware. So depending on the model, the GPUs that you want to run this model against might be very different. And that's the role that compute orchestration plays, and it plays a huge role in efficiency as well. Lastly, the hardware itself. So this is where your actual model training runs. And what we've noticed is that with hardware rapidly evolving in AI, being able to adopt the latest hardware becomes important, and we also want to move really fast in that area. So ML application development, how we do it at Pinterest is through an SDK that we internally called MLenv. You can think of this as very similar to PyTorch Lightning or Hugging Face Accelerate. What ML engineers are responsible for is just writing their PyTorch modules. They can optionally write a trailing loop. Everything else is taken care of by this SDK. So what is everything else? So this is about how we integrate with our data ecosystem, and then we can convert data at rest into tensors that PyTorch understands. We provide metrics around how efficient your data loading is. And while training is happening, there's automatic integration with an experiment tracking tool like MLflow. And we also make it really easy to go from training on your local dev instance and moving that to a cluster of machines, all that with a simple flag. And once your model is trained, you want to make sure that it's in the right format so that the serving clusters can pick it up and it has the right metadata. And we also have optimizations here about enabling quantization. Now, the way ML engineers develop these models is on a Python monorepo. And the nice thing about this is we have our applied research community who are looking to build state-of-the-art techniques. So once they've made it available and tested, it's available for everyone to use. And the way we typically productionize these state-of-the-art techniques is once it's available for one use case to use, we make sure it's optimized. And then once it works well, it's pretty easy to adopt for other use cases as well. With having a monorepo, what's also good is that we have built out the CI/CD infrastructure for ML training applications. So for example, if we upgrade PyTorch, we are able to run a full integration test suite and make sure that ML trainers don't break. So what this happens to the ML stack is what is user-owned is just a training application. Everything below that is platform-owned. So one of the consequences of this is that the platform has full ownership on the version of PyTorch, Ubuntu versions, CUDA versions. So it's imperative for us to move fast. That way, we make sure that ML engineers who want to train state-of-the-art models have the right PyTorch version. We're also looking at making sure that we have a stable version which tracks the latest release of PyTorch and a nightly as well, so that if a commit lands in PyTorch, we're also able to absorb that. So yeah, that's about ML training application. Next is the ML compute orchestration. As I said, once your training application is built using Docker, we want to target that to some hardware. Internally, we have a platform called Training Compute Platform. This is built on top of our internal Kubernetes team. We also are able to target AWS Batch as another compute backend, and I'll talk about that a little later. So Training Compute Platform is able to give users a job management UI, metrics, logs integration, hyperparameter tuning is also implemented here. People also have access to ML-aware dev servers. So what this is a pre-packaged developer environment where people can iterate quickly. And I just want to call out one key feature that we have around resource management and scheduling. We worked with our partners in the compute platform team to implement per project quotas to say how much GPUs a given team has access to. We have two concepts here. One is about guaranteed resources for GPUs. So this is a minimum amount of GPUs that's guaranteed for every team. And on top of that, they can extend to a max, which is a shared pool of GPUs. Moving forward, we're also trying to see how to enable preemption and gang scheduling, simply because gang scheduling becomes really important when you're training distributed training workloads. One other interesting consequence about having a unified orchestration layer is that we have a data set of all the jobs that were launched at Pinterest, the corresponding configs, which Docker images they used, and we take a dump of all of this and make them into partitioned Hive tables. So these involve the Kubernetes specs, the time series databases, which has all the metrics for this job, MLflow experiment. So all of these, once available as Hive tables, we are now able to do offline analysis and really provide intelligence around things like, which use case is using the most amount of GPUs? How much are they wasting? We are also able to reason about job failure rates and which use cases we have to optimize so that there is highest ROI depending on how much you're spending. So this has become like really valuable for us to make data-driven decisions around capacity planning as well. Finally, it's the training hardware. Now, we run on AWS, and we've been on AWS since the beginning. In 2018, we started off with training on CPU-like instances, and these were linear models. We still use distributed training, but the models were small enough, and the goal was just to train on more data. But then as models got bigger, we started adopting GPUs. Around 2022 was a phase when we were fully on P4Ds, but then that became pretty expensive, as you can imagine. We realized that not all use cases actually need P4Ds, so we diversified our GPU instance strategy to also include the G5 instance family for ML training. The advantage was that, of course, cost came down, but it's also that the G5 instance family is what's used for serving as well. So once we are able to share the same underlying instance family for training and serving, we are able to really make sure that a common set of instances are available for both. So yeah, next I want to talk about two case studies. One is about how we've scaled distributed training for the two use cases. First is recommendation models. Our recommendation models follow a typical pattern found in the industry today: transformer models with a combination of dense and sparse features. They are trained on 18 to 16 GPUs, depending on the use case. Now, the challenges for us are actually threefold. One is these recommendation models typically train on large data sets, so 17 to 30 days of data. And then we also have to deal with ID embedding tables. Now, these become important when you have sparse features. And then you have these large embedding tables, which don't typically fit in a single GPU. So we have to figure out how to shard them. Then finally, one other interesting leverage that ML engineers typically use to get performance boosts is iterating on the data set itself. One example is ML engineers may want to change their sampling strategy for their data sets or change how they weight the different rows of the data set. So all of this requires data pre-processing before feeding it into the trainer. And that's also an area of challenge that we have to solve for. So if we go one by one on on what works well for us, first is handling large data sets. PyTorch has a wrapper called distributed data parallel training, which is pretty standard in the industry right now. So this is great for us to train on larger amounts of data. So what typically happens is you have your model replicated across multiple GPUs. So this is the full model itself, except that your data is sharded across these GPUs. And then during your backward pass, there is a gradient all reduce step, which makes sure that your gradients are sync across all the GPU devices. And then you just go to the optimizer step, and it's all over, and then your data is fed back again. This works fairly well, and we've been able to productionize a lot of models using distributed data parallel. And if your embedding tables are small enough, this is mostly enough. What happens is if your embedding tables become bigger, then it may not fit within a single GPU. And as an example, when you build recommendation systems, you want to represent entities like products or users. So as you have lots of users, you want to represent them as embeddings. So as an example, if you have 200 million entities, each with an embedding dimension of 64, we're talking about 50 gigs of memory. And that's fairly big for any GPU to handle. So one common practice is to shard the embedding tables across the devices. And for this, the PyTorch community has a library called TorchRec, where we are able to shard embedding tables. So for us, this involves being a combination of using TorchRec to shard the embedding tables and still use data parallel so that we can train on large data sets. Next is data set iteration. Again, like I mentioned, users want to iterate on how data sets itself are processed before feeding it into the trainer. Here, there are 3 examples. On the very top, this is just a basic read. So whatever your data set we have in S3, that is just read and fed into the trainers. One interesting pattern is people may want to do things like spam filtering, right? We want to make sure we only train on non-spammy users. So this involves writing a filter function when you read your data. As you can see, these are CPU-intensive operations. So the throughput for training drops. And if you add additional like data pre-processing, like spam filtering plus hard negative downsampling, your throughput drops even further. When we looked at why throughput dropped, it was because on the GPU instance, we were being throttled by the CPUs. We just didn't have enough CPUs on the GPU instance. So we wanted to see how to decouple the data processing layer and the GPU compute layer. And that's when we looked at Ray. Ray is an open source framework which is used to build distributed Python application, but it's a great fit for ML. So what we've done is we spawn up a single Ray cluster, which has actors for CPU pre-processing, and then for GPU separately on separate instances. And what this means is we now have a data pre-processing fleet of like n CPU machines, which are all doing data pre-processing steps and pumping data into the GPU. And the advantage of this is we are now able to drive more throughput because your GPU utilization is high. In terms of numbers itself, here you can see for one particular data pre-processing use case. The simple read on the orange is Torch, blue is using Ray. Simple read, that's your baseline, but then as you add more complex data pre-processing, the training time increases by using just Torch everywhere. But then if you use Ray as a solution, the training runtime doesn't increase as much. Similarly, you can also see the cost per job doesn't grow as much when you use Ray. So this has been a pretty successful way for us to scale data set iterations. The next class of models I want to talk about is content understanding models. Again, here the model sizes typically start getting bigger. Like one example is a unified visual embedding. So the use case here is given images at Pinterest. We want to represent them using embeddings. Now these take a fairly long time to train. One of the limitations is that because these models are big, they don't fit in a single GPU. So some things like distributed data parallel training becomes infeasible because the model is just too big to fit in a single GPU. Again, PyTorch has this library, has an extension called fully sharded data parallel training, which is a perfect use case for this. In a sense, it's somewhat similar to distributed data parallel training, except that instead of the entire model being loaded into a GPU, we're able to shard the model across multiple GPUs. And what happens is during your training phase, when a single replica needs parameters that it doesn't hold, it talks over the network to fetch the parameters, and it does whatever it has to do in the forward pass or in the backward pass. All these parameter exchanges happen over the network if you're doing multi-node training, and it uses NVIDIA's NCCL collectives. But what all this means is that when you want to do FSDP over multi-node training, network typically becomes the bottleneck. And what we've noticed is that we need some sort of HPC-style internode networking with the following properties: low latency, GPU direct RDMA, so that your NCCL collectives don't go through the OS, full bisectional network connectivity, which is non-blocking and non-oversubscribed. And this is where Ultra Cluster was a perfect fit for us. Ultra Cluster is a deployment of GPU machines in the same rack. It also comes with network devices called EFA, which enables 400 Gbps of internode bandwidth and GPU direct RDMA. And the way we've deployed it is all this needs is for the Nickel version to be built a certain way to include PyTorch. So from a user standpoint, they actually don't really have to change anything. It's the same training application. Because we own the underlying Nickel versions, we just build Nickel with EFA and libfabric. And the compute orchestrator is now able to target an ML application to the Ultra Cluster. So that way, we're able to make this change without any user involvement or any user-side code change. The results are pretty good. For some of our large model training jobs, we've seen a 2x speed up. And what you see here is the GPU utilization. So we're able to actually saturate the GPUs pretty well. And this is another model which also saw a 2.5x speed up by using Ultra Cluster. Yep, and the next case study I want to talk about is updating the ML stack. Now, why this becomes really important is, as you know, like there is a new development in the ML world every day. Like new models are coming up, models are getting bigger, and a lot of the innovations are also around, okay, how do you make sure models are trained and served efficiently? A lot of the optimizations that we care about, or the industry also cares about, typically make their way to PyTorch. One example is scale dot product for fast transformers, flash attention. All of these make their way into PyTorch as an implementation. So being able to upgrade PyTorch versions reliably and quickly is very critical for us to make sure that we are able to train models and serve them efficiently. So here are just a list of wins that we got by just upgrading PyTorch, right? And we're currently on PyTorch 2.0, and that's also what is enabling us to build a lot like bigger models using FSDP. Now, if you look at what it takes to upgrade PyTorch itself, it's like it has a bottom-up dependency. So PyTorch will be dependent on certain versions of CUDA. Certain versions of CUDA will be supported on some NVIDIA drivers. So we have to update the drivers first, and then build PyTorch against CUDA libraries, and then make sure it's available to the training applications. So how we used to do this was we had 3 separate serving fleets. We had ML developer instances, ML serving fleet, and ML training fleet. All of them use separate AMIs. And what this meant for us as ML training infrastructure was we had to work with the teams individually to get the NVIDIA drivers upgraded first, because that was the first step in the process. Now, this involves putting this task on another team's roadmap, making sure it gets done, and there might be like nuances in how they build the AMIs. So this became a cumbersome process, and it also has to be like tested separately. So we wanted to have a single like unified AMI that works for all GPU instances, and that's where we partnered with the AWS DLArmy team to have a shared base AMI. So this shared base AMI is what we have for all of the ML developer instances, ML serving fleet, and ML training fleet. So this gives us the NVIDIA drivers that we care about. And then this base AMI is then inherited to form the different instance-specific AMIs that we care about, for example, for training, serving, and developer instances. So this helped us reduce the total cost of ownership and make sure that we're able to roll out PyTorch versions 3x faster. So some takeaways for us is, standardizing the ML stack can result in faster upgrades to the ML stack. And why this becomes important is, if you want to build state-of-the-art models, you want to make sure everybody can move fast. And with standardization, once you have a certain number of ML engineers, you don't want them spending time on ops. So making sure that a single version of PyTorch or everybody is on PyTorch really helps. For recommendation models, they benefit from a combination of distributed data parallel, distributed model parallel, and remote data loading via array. Billion-plus parameter models for us can benefit from using FSDP. And for us, using ultra-cluster became a game changer because we saw the speed ups 2x to 2.5x. And using well-tested offerings like DLArmies and DLCs do reduce the total cost of ownership, and of course also make it easy to upgrade the ML stack. So just some impact, we have 2x speed up in using large model training using ultra-cluster, 3x faster to roll out hardware upgrades, and the total cost of ownership has also come down by adopting DLArmies. Yeah, that's mostly what I had for my section of the talk. I'll now hand it over to Zlatan to talk about the solution architecture.
Hi, everybody. Name is Zlatan. I work with Kartik's very talented team with Pinterest and try to help them build all these wonderful things that they were talking about. So what were we closely work with our service teams to kind of build out features and things. And this is kind of fairly key as well for all of you and how effectively customer obsessed we are, because we take actually what you tell us and how you want us to build services, and we build them accordingly. Batch was not really primarily an ML type platform that was used, and it was just seen as a very simple way to actually create jobs, stack those jobs up, and then create dependencies for the jobs and create multi-node processing jobs, and start creating fairly simple definitions for them. So you could have direct sequential dependency within the job and how it works. But kind of taken more with your container image and your IAM roles and mount points and parameters that are kind of defining how the jobs are going to be executed. But as we kind of extend that into orchestration, what's really important is that how these jobs, and what was really important to Pinterest, number one was, hey, don't treat the job submission as like multiple different processes that are running within the cluster. It has to have a concept of a job and understand that this job is running as such across multiple different nodes, and those nodes could be different types of hardware themselves, right? So they could be heavy network I/O, they could be GPU intensive, they could be memory intensive, and so on and so forth. And we're going to kind of prevent that asymmetric use of resources and really kind of distribute the load as it should be to have the properly saturated utilization of these resources, and that way also run very cost effectively and sustainably at the same time. So that also depends very much on mitigating all the infrastructure issues and how we deal with our compute environments specifically. So there was number of different updates, things like min vCPU update, making sure that the instances effectively that are running. First of all, they're running in ultra cluster. Ultra cluster means that you have high density compute, clustered environment that runs on the same spine, and as such, those instances become dedicated for use, in this case to Pinterest. And we want to make sure that none of them actually fail, and if they do, that we can mitigate those risks and issues. And when the MNP jobs are run, that the actual compute and all is taken into account, including the GPU resources, so it doesn't actually run out of them. And we have things like proper tiering. With respect to the job. So one of the requests that came from Pinterest is like, hey, we want to actually have different tier jobs, and then you probably heard Kartik as well mention things like preemptive and reserved tiers, right? So we want to reserve tiers of the resources that are going to be used by different ML teams, but at the same time we want to have also this preemptive queue where they can actually dip into this pool of resources, but should a more important job come, we want to take away those resources back and reprioritize the more important job that has this appropriate priority. And this is where the fair share scheduling feature came with Batch, and I implore you to check that out specifically, as well as, like I said, min vCPU. And then, ability now to consolidate and view all the runnable jobs and select which instance types and, we want to use and how you want to use it, and kind of how you want to run across multiple different compute environments. The way that the actual cluster works is that it's kind of defined by the agents that are running on the instances itself, and kind of how they signal themselves to the control plane. So that's why it can actually support different types of and different hardware architectures underneath. And throughout working with Pinterest, we managed to work on making submission of jobs 1.6 times faster. Behind the scenes, the actual submission to the job schedule was 2 times faster. We worked on scaling up resources which became five times faster and a lot more reliable, as well as the execution of the jobs which became 2 times faster. And that's kind of hand in hand with the solutions as they're being built and kind of working with, in this case, with Batch service team and optimizing how this actually gets executed. One of the key things are, and I don't know if you're familiar or not with it, but is ODCRs, or on-demand capacity reservations. So what those allow you to do is actually to create and reverse capacity and manage your capacity, not just via, normally it was through savings plans and, reserved instances. This way you can actually just ad hoc create and reserve capacity based on the availability zone, instance type, tenancy, OS, or anything else. With respect to what was key for the solution for Pinterest was actually creating custom ODCRs that would reserve instances within the same spine to provide optimal latency between all the P4D instances. And I'm going to kind of get into that specifically. And also to make sure, obviously, that none of those, as any of those instances actually get shut down and all that, they don't actually disappear and can come back up and be reused over and over. And that way, ensure that capacity remains on that same spine as it needs to be used. And kind of the overall architecture, the way it looks like, you'll see that the Pinterest managed Kubernetes or the Pin Compute team, this is kind of where the orchestration lies, and then it uses and submits jobs directly to Batch. And as such, it really kind of simplified and abstracted away a lot of, as Kartik said, a lot of complexity away from data scientists and ML practitioners and all that, allowing them just to focus on the jobs that they're executing, and then through means of parameters and attributes effectively do define both the affinity as well as the jobs and specific queuing necessary for how those need to be executed on Ultra Cluster. Within Ultra Cluster, we have that EFA or Elastic Fabric adapter, which underneath really uses the NVIDIA collective communication libraries directly to scale up the GPUs very quickly. And on the other hand, it uses the GPU Direct RDMA to provide this ultra low latency between GPUs, between different P4 instances. Right, those are your A100 instances as such. And that was that actually, and on the other hand, another thing that is very, very unique about Pinterest is that they have a very bold and amazing strategy to actually use object storage strategically for everything they do. And so for their training, they're actually using the training data sits on S3, right? And it actually goes and gets streamed into the instances using instance store. These are the I4I instances. And it's basically as it's caching, as it's streaming, they can actually use it, very effectively. We are working with S3 team, and there's going to be some announcements as well on some of the new features and things that are going to improve that quite a bit. I'm not going to take away from that because that's yet to come. I think on Wednesday in the afternoon. But yeah, that's very unique because usually you'll have customers using FSX and other things, file systems and all that, and that's not what we're doing here. So that's something that is very unique, specifically here. Another thing is, Karthik talked about the different types, and these are the different types of large-scale models that are being used. So the compute intensive, they're like 1 to 7 billion parameters. They're using cutting-edge models. And you've seen some of those examples. They take weeks to train from scratch, and they really take advantage of the NCCU, right, of the low latency GPU to GPU, and they're fairly important on that end. And that's when is when Karthik came to me and says, this EFA that allows us 400 gigabits per second, you know what? We need 1,600 gigabits per second. We need 1.6. It's like, fine. And P5s and H100s just came, right? It's like, no, we actually have 3,200, 3.2 terabits per second now. That's probably when you come next year when we talk to you about implementing P5s, it'll be very exciting. But this is why it's fairly Q and why the throughput, latency is very important, low latency from this perspective, but throughput is even more important, right? And then you have the graph neural networks. Honestly, Pinterest is in my personal opinion, leading the pack in this sense, and they're really shaping the industry on how these are the models that they've used for years, and they've perfected it. There's many publications, and there's going to be links to their blog, which I implore you all to listen to and to read up on those that have actually defined how many other companies, customers, even ourselves, using graph neural networks. That also runs now on AWS Batch, and then there's visual transformers, just the same, 1 billion parameters. So on the graph neural networks, that runs really kind of on a heterogeneous mix of instances. So it's not just P4Ds and all that. That's kind of really spread across multiple different instances. Visual transformers, things like unified visual embeddings, just the same. A lot of really papers that Pinterest has written are pretty amazing on that end. That runs on the Kubernetes infrastructure. It's fully sharded data parallel, way of running that Karthik was talking about. Their core models take months of long training, which actually is fairly key then to provide reliable way of doing so and consistent way of doing it. This is kind of where it kicks in from reliability and consistency perspective. So since we kind of in the last 10 minutes, the key takeaways on this end, we've built key features specifically, and working with Pinterest has really altered our roadmaps for several different teams. One is the Asimov team that was speaking Arindam, and another one is Batch and Ultra Cluster EC2 team, and all things like fair share scheduling, mean vCPU, dynamic compute environment updates, 7-day job retention, scaling improvements to reduce the idle and underutilized instances. Things like what we yet to release is working on one view into issues from a monitoring perspective. Is like, hey, we want to see if the job failed, why did it fail, all the way down to the lowest hardware level. And we continue to build up more and more support. Another one is Batch working on EKS, which is fairly important because that's kind of going hand in hand with adoption of EKS within Pinterest as a platform. Again, latency versus throughput, I talked about that. Orchestration, fairly key, scheduler, and everything we talked about. The DL armies and DLCs have really made all the difference. You saw the numbers. And then fairly key, once again, the streaming data from S3 and how it works through instance store caching with different formats. They primarily use Parquet. And like I said, one of the key things is that as soon as this was ready for them to use, they were able to onboard other teams like the ATG and other very quickly. And it didn't require any specific training. They put it up on the wiki, and people were able just to read through and just start using it straight away. And that is absolutely amazing with very, very kind of limited support and all that. So very quick, very good. And with that, thank you very much. Like I said, my name is Latan, Arindam, and Karthik. Last but not least, please ask us any questions that you may have on everything you've heard. Yes, I can go one. This is the resources you want to take for sure. So do take a picture of that. I think the first one is the blog, is the link to Pinterest publications. So as you're taking pictures, if you have any questions, please do ask. I was told that there will be a microphone, but otherwise you can also come through and ask us if we end the session now. Thank you.